Tomorrow we're going to launch rockets or something. Anyway. What else we got here? All right, I'm going to, that should be good. So I'm going to record here just kind of a current review. If we look back at, I'll share screen real quickly here. So this is what we're looking at today. Review for exam 3. We'll see how time goes. We should be able to at least, there's one additional topic in chapter 7. I'm going to look real quick and see what, stop share. Look and see what microphone I'm using on Zoom here. Okay, that's fine. I don't want to yell at the document. So again, we're going to finish. There's one last topic in chapter 7 we're going to finish today. It's isentropic efficiency. That doesn't show up on this exam, but it does show up on the final. And then after that, as time allows, we'll start a little bit of chapter 9. That's ideal cycles. So it's looking at Otto cycles and Giese cycles in chapter 9. As time allows, and on Thursday we might get to a little bit of chapter 10, that the Rankine cycles. Then we'll see. And the next week is our last week, right? So we've got Tuesday. We'll review for the final, and then we'll tidy up anything on chapters 9 needed. And if we have time, we'll do something in chapter 10. And a week from Thursday is the final exam. So that's all we'll do on that Thursday. So that's coming up. But yeah, so Thursday we'll take exam 3. We'll go from there. Now, logistics on exam 3. So logistics on exam 3, just like any other exam, it's going to be just a couple of chapters. For us, it'll be chapters 6 and 7. Up to isentropic efficiency, not including isentropic efficiency. That shows up on the final, but not on this exam. So up to isentropic efficiency. What do we got here? We got 4 problems. As per usual. I'm aware of the amount of time that these problems consume. We talked about how I grade. You guys have seen how I grade. Hopefully that helps some of the time consumption, right? But I'm aware getting 4 problems done in 75 minutes at this level is a challenge. So that's the reason on exam 3, I like to give you the option to take 1 problem home. So you have the option to take one of those 4 problems home. So 1 problem per page, just like normal. You can either remove the staple, pull the page out, re-staple, or if you comfortably tear it out, that's fine. Remove one of the 4 pages, take it home, bring it back to the next class period. That'll be Tuesday. It'll be our last class period. So bring it back the next week from today. If you take a problem home, I tend to grade those a little harsher. Normally what I do in general is I'll round down to the nearest 5. So kind of keep in mind, if all you've got is like a unit error or a sign error, and that's the one mistake you make in the entire problem, on a test problem, that's normally just a point or 2, right? It's not too big a penalty. If you take home a problem, I'm going to assume that you're going to take your time, polish it up, get your algebra and units right. I really try to work to get that one right. Use your resources you've got available. Don't give me check solutions or any other online resource. I won't grade those, right? I don't mind you using those as a tool if you're responsible about it. We talked about that multiple times. But if you just give me a verbatim solution that I can find anywhere on the internet, it'll be a 0. But otherwise, as far as grading of take-home problems, as long as you don't give me a verbatim internet solution, just be aware that a simple error that would normally just cost you a point or 2, if I'm looking at the paper, I'm like, all right, well, that's a 22, you're going to get a 20. If I'm looking at it like, all right, that's about a 17, 18, it's like a C, you made a couple of major errors, that's going to get rounded down to a 15. So basically I go 25, 20, 15, 10, or 0. once you get on, if you take a problem home. Now, whether you turn in 3 or 4 problems that day, the problems you turn in that day are graded normal, absolutely normal. So there's not necessarily any penalty to take a problem home, except for just understand, take your time, work it out right, because a small penalty can get magnified on taking a problem. Questions about, does that make sense? So if you got, and kind of the general rule of thumb is, if you look at the problem and do I take this home or not? Well, do you think you could earn an additional 5 points? Taking it home? Or you think you're in that 15 to 20 range? You're not completed, but you know how to get to a solution and take it home. If you've got a solution and you're pretty comfortable with it, turn it in. That's hopefully that helps, right? So second guessing a problem, feel free to take it home. If you're second guessing multiple problems, well, that becomes a choice you have to make, right? But anyway, other than the option to take a problem home, the rules are the same. It should look like just any other exam. Open book, calculator. Talk about calculator rules. You're reading PDFs on your calculator. You want to mine instead. As long as it can't access the internet wirelessly, if you've got an issue, we'll have a conversation. One sheet of notes, up to 8.5 by 11 inches. Front and back is just fine. Whatever you can physically write in your own handwriting is just fine. Standard. Okay. As far as then what's on these, what are the topics? There's the notes here so I don't miss something. So, mention chapter 6. This is chapter 6. I like to say is this introduction to the second law without ever actually showing you the second law, and it's basically based on this idea. The second law is formed based on 2 major ideas. Several ideas coalesce together during this time frame where we're trying to get the most energy we can out of these engines. The 2 main ideas really emerge and evolve. We credit Clausius with one of them. We credit Kelvin and Planck simultaneously with the other one. I don't remember which is which, and these are not verbatim from the text, but roughly they say something like this. One statement is that a device in a cycle, a device operating in a cycle, cannot produce net work by exchanging heat with a single body. What does that mean? Well, if something's operating in a cycle repeatedly, and if we can maintain conditions, we could operate it perpetually. Basically, what we're saying is you can't, if I could exchange heat with a single body and produce net work, that means theoretically I could convert all heat to work, which we are just almost certain we cannot do. The third law of thermodynamics provides a possible route to do that, and we just don't think there's any way of maintaining absolute 0 while dumping heat on something. Could, maybe, but again, this is just kind of, this is observation that we've made. We're unaware of a situation where I can convert all of heat. If I'm exchanging heat with a single body, that means I'm absorbing heat and producing that work, and that's it. We don't think we can do that. I think we're going to have to reject remaining heat to maintain a cycle, to keep the cycle going. We're going to absorb more heat than we can convert to work, so we're going to have to reject the remaining heat to complete the cycle. Okay? And that's also, so a similar idea emerges. Device in a cycle cannot simply exchange heat from the lower temperature body to a higher temperature body. That can't be the only thing it does. It has to do something else. The common thing that we do is we just basically add some work to this device, as we would in a refrigerator, to keep it. Now, we have this idea of a perpetual motion machine. And this is a device that violates first or second law. In theory, it could violate the zero law or the third law also, and be considered a perpetual motion machine. We're really focused here on the first and second laws. It's going to be our, we talked about from day one. It's going to be our focus. So what does that mean? You know, we can't construct a device that violates either of these laws to the best of our knowledge. So call me if you figure that out. I don't think that's going to happen. What we can do is we can propose devices that, in order for them to exist, would violate one of these two laws. Okay? So what does that look like? Well, if it violates the first law, that means it's either creating or destroying energy. If it's violating the second law, that means it's, we understand now, that means it's destroying entropy. You have negative entropy generation, it's destroying entropy. What that could also mean is it could be more efficient or have a higher performance than an actual device that doesn't generate entropy. Okay? So if a device has a higher performance or efficiency than a device that conserves entropy, that doesn't generate entropy, that means the only way that occurs is if the device is destroying entropy, which can't happen. So there's two main ways we can determine that. One is if I can determine the maximum efficiency or performance for a device, and we have something that appears to be more efficient or better performing than that, that's a violation of the second law. Or if we can measure somehow the entropy generated, and we find that to be negative. That's the other way we know it violates the second law. Right? So those are kind of our checks there. One is a chapter 6 check, the other is a chapter 7 check. So what causes that? Well, we've got irreversibilities. Irreversibilities, these are what, simplest way to put it is, it keeps us from restoring system and, big and here, system and surroundings to their initial state. So if something's irreversible, if it cannot be reversed, that means, what that means is now there's entropy has been generated. We understand that now from chapter 7. Entropy has been generated somewhere in the universe. Where is that entropy at? That entropy could be in my system, or it could be in the surroundings. But in either case, there's now more entropy that exists than when we started. We can't ever get rid of that. It's irreversible. We can't go back to the state before where I have less entropy in both my system and the surroundings. I can get the system back to its initial state. I can get the surroundings back to their initial state, but I can't get both. it's irreversible. Okay. So these are irreversibilities, things that do that. What are common things that do that would be friction. In general, anything that turns work or nice orderly energy, mechanical energy, into a thermal form like heat. Anything that does that is typically irreversible. Because again, that heat is a chaotic form of energy. That's a higher entropy. So if I turn work low entropy into high entropy heat, I can't go back to the initial state. And then the last thing to mention here, and then we'll talk about some devices, would be this idea of the Carnot cycle. Carnot cycle we often credit as one of the first, if not the first, one of the first reversible cycles that was proposed. Here, so the Carnot proposed this idea of this reversible cycle. It can be used as a heat engine, and because it's reversible, it serves kind of as this ideal situation, this best case situation. It would be if I could operate something that was completely reversible, that means I could get both the system and the surroundings back to their initial state. And so what it does is it sets the limit for engine and refrigeration performance. Right? It sets the limit for engine and refrigeration performance, and that limit we find to be a function of temperature only. So temperature is the only driving factor. Now, we see that when we actually derive these expressions. So let's look at some of these devices that we would apply something like a Carnot cycle to. So devices we would apply this to would be something like a heat engine. The heat engine is a device that's going to absorb heat from some high temperature source. That heat coming from that high temperature source is going to be absorbed into some sort of a heat exchanger, a boiler typically. So the boiler is going to have high temperature air being blown over some kind of a coal fire or natural gas fire, or maybe high temperature water coming out of a nuclear reactor. And then, so you're going to have a hot stream coming through this heat exchanger, and that's going to add heat to a cool stream. Right? So you're going to have two separate streams, but we're really only going to focus on this stream that goes around the engine. And so we're not as concerned about how does the boiler add heat. We just say it's adding heat from the high temperature source. That's going to boil off high pressure, high temperature. Typically, we're going to use steam, right? And that steam is going to run into this turbine at high temperature, high pressure. That turbine is going to expand that fluid as it flows through. It's going to expand and slow it down and allow it to cool down, go to a lower energy state, and as it does it, it's going to pull work out as a turbine does. So the turbine's going to pull work out. And then low pressure steam, probably a fairly high quality, 95% quality or higher, maybe even superheated vapor is going to come out with a lower energy level, lower pressure, lower temperature is going to come out of that turbine. That's going to run then into a condenser unit, another heat exchanger. Have reasonably warm but low pressure steam coming out of this, and I'm going to expose it to some cold stream. So it's going to lose heat then to some low temperature sink. Maybe the atmosphere, maybe a lake or a river. Too much. Maybe a lake or a river, something that's at a lower temperature. So it can then absorb any remaining heat to complete the cycle. In a modern steam engine, which is typically in a large power plant, I'm going to try to get the fluid all the way down to a liquid, working fluid all the way down to a liquid. So when I do that, then when I run that through some kind of a pump, that pump's only going to need just a little bit of work in. Why do I need to do that? Well, I need high pressure going into the turbine, and there's nothing in the boiler that's going to increase the pressure. I need high pressure before I get to the boiler. We're going to assume ideal boilers where there's essentially no pressure loss. So there's nothing going to cause the pressure to increase in here. If anything, it's going to drop. We learn about that in the fluid mechanics class. So I need high pressure going into the boiler because I need high pressure going into the turbine. So how do I accomplish that? Well, by simply putting a little bit of work into a liquid, and that increases the pressure very quickly. So again, if we look at the first law for this device here, I've got work in minus work out plus QH minus QL. And because it's a cycle, your delta U in this case, it's a closed system, but it's also a cyclic system. So the change in internal energy for the entire engine, we want that to be zero. We don't want this thing to blow up. If delta U is increasing, it's going to blow up eventually. If delta U is decreasing, it's going to exhaust out eventually. We want it to operate perpetually in a cycle if we can maintain the conditions. So we want delta U to be zero. Okay. So what that essentially tells us is basically the net heat in, the difference between QH and QL, is going to equal the net work out. The difference between work out and work. And then we mentioned up here about the Carnot cycle. The Carnot cycle being a reversible cycle, it sets the limit for engine and refrigeration performance. Okay. Well, how do we measure the performance of an engine? We measure the performance of an engine as what we call the thermal efficiency. That's the ratio of, efficiency is typically what you want, divided by what you have to do to get it. What we want for an engine is we want the net work out. The other side of that ratio then is what we have to do to get that net work out. That's QH. And if I substitute this in, this QH minus QL in for the net work out, this simplifies down to 1 minus QL over QH. As we mentioned, the Carnot principles dictate that the maximum efficiency for this heat engine then is going to be based on the temperatures. And so what we find is that the ratio of the temperatures, and we can prove this here in just a little bit if we take the second law as true, we can prove this in just a little bit, where the ratio of heat transfers is equal to the ratio of temperature. If it's reversible. In this case, if it's Carnot or any other reversible device being the best possible version, then we can show that the ratio of heat transfers should be the ratio of temperatures in that best case scenario. Questions so far? So that's for a heat engine. We looked at some other devices. We talked about a refrigerator. Memory serves, I think it was Kelvin and Planck came to the conclusion that you can't simply move heat from a low temperature body to a high temperature body. But we have devices that do that. The way they do that is they do something else to make it occur. Normally what we do is we're basically pumping the fluid in such a way that it also pumps the heat. So what I can do, draw a compressor here. I like to draw the opposite of a turbine, where I put work in and the output comes out of this narrow end. So it's basically coming in down here, the wide end, and it gets squeezed down through some sort of an impeller blade at the narrow end. And it gets squeezed out at a higher pressure. And if it's coming in as a vapor, as you squeeze it, you'll also increase the temperature. And that's our goal for a refrigerator compressor, is to increase the temperature. So if we get it so hot that I run this through a condenser on top, again, just a heat exchanger, This is the big set of aluminum fins outside of your air conditioning unit. If you walk by an air conditioning unit that's running outside, you feel the heat coming off. That's this QH here that's going to this high temperature body outside. If you're dealing with a refrigerator in your house, that's the warm air coming off the back of the refrigerator, off the coils in the back. That's your condenser unit emitting heat in the high temperature unit. How does it do that? Well, again, your compressor is going to increase the temperature of this refrigerant to the point where it's hotter than, it's at a higher temperature than the high temperature source that you're rejecting that heat to. So there we go. Now, what we do after that, so now I've got high pressure fluid coming out of this condenser that's been cooled down. It's probably going to come out at a high pressure liquid, or at least a liquid vapor mixture. And what we can do is we find if we run that through some sort of device that's going to drop the pressure, allow this fluid to expand, you'll also drop the temperature. A safe, cheap way to do that is through a device we call an expansion valve. Again, a lot of times if I achieve the speed of sound here at the choke point and then allow it to expand back out, it allows that fluid to then cool down. And again, think about a compressed can of aerosol, like electronics cleaner or something like that. If I hold that open for a long time, allow that fluid to expand, it gets really cold. Similar things happening here. If I allow that fluid at a high pressure to expand out, it goes to a lower temperature. And it will get so cold after that process that it'll actually then absorb heat from the low temperature source down here on the bottom when we run this through what we call an evaporator. So if you're looking at your air conditioning unit, if you've ever had to replace filters on a central heat and air system, those filters are going to be just right next to your evaporator coils, which are going to look similar to the outside coils up here on the condenser that are emitting heat. These evaporator coils, that's where the cool refrigerant's going to flow that then you can use to cool your house. You won't see them in your refrigerator, your household refrigerator or freezer too often unless you take it apart. I don't suggest you do that unless you're trying to fix something. Even then, you pretty well need to know what you're doing. Those plastic clips break too easy, in my taste at least. Anyway, I digress. It's a refrigerator, at least a basic schematic of a refrigerator. So what do we got going on here? If we look at the first law, I've got work in plus QL minus heat out is QH. And again, that's equal to, it's a closed system. All the refrigerant is trapped in it. That's equal to delta U. If it's operating in a cycle, that refrigerant will return back to its initial state eventually. So that cycle should operate where delta U is 0 over the entire cycle. So your work in should equal essentially your net heat out, if you will. That's QH minus QL. We measure the performance of a refrigerator based on what we call the coefficient of performance, because this value can and often does exceed 1. We limit efficiency only to things that cannot exceed 1. So we call this a coefficient of performance. But it still is the basic idea of what do you want, in this case, Q sub L, divided by what do you have to do to get it, that's work in. And if we substitute in right here, QH minus QL in for work in, this simplifies down to 1 over QH over QL. That's 1. As we saw earlier, we said that if this is the maximum performing device, meaning it's a reversible cycle, then that ratio of heat transfers becomes the ratio of temperatures, TH over TL minus 1. And that tells us what the maximum performance for this device would be. And then the last one we talked about would be a heat pump. You can redraw your refrigerator if you like. It's the same thing. It is a refrigerator. You've got work in, your
pushing heat, QH, out to a high temperature source, and you're absorbing QL down here at a low temperature source.
That's all I'm going to draw of a refrigerator because it's the same exact schematic. The setup's almost the exact same as what you see in a refrigerator up here. Components are essentially the same. Some heat pumps will actually serve as a refrigerator. You can just run them in reverse. My wife and I just bought a compact little refrigerator that we can keep. She's got some stuff she needs to keep refrigerated, but it also works as a travel device. And it has a hot and a cold mode, which tells me it's one of these that you can just run it in reverse. You can just reverse the direction of the flow, and it will either heat or cool the contents of that device. You can plug it into the wall, or you can plug it into your car, 12 volts. I was impressed. I've not tried the hot mode yet, but I assume it's just running it as a heat pump. That's what it's telling me. Same first law. The only difference here is what you want. So if I measure the performance of this device, whereas with the refrigerator, my numerator is Q sub L. That's what I want, is Q sub L for a refrigerator. For a heat pump, what I'm actually trying to do with a heat pump is I want to heat the high temperature source. That's my goal. That's my performance. That's what I'm measuring this based on. Now, what I have to do doesn't change. I still have to put work in. So my denominator is the same. Which, by the way, if you look at what's going on here, this is QL plus work in combined to become QH. So we know for sure QH is greater than work in. COP for a heat pump, you see that? COP for a heat pump will always be greater than 1. Always. Because QH is always going to be greater than work in, because QH is work in plus QL. So this always has to be bigger than this one. So this is always bigger than 1. So this, we cannot, COP for a refrigerator, a poor performing refrigerator might be less than 1. COP for a heat pump is always greater. So the reason we don't call them efficiencies is because they can exceed them. If I substitute this expression up here, because it's the same first law for this device, so I substitute that in for work in down here, rearrange that equation, divide everything by QH looks like, this becomes 1 minus QL over QH. And again, if I'm looking or analyzing the best case scenario, reversible, so that could be a Carnot or any other reversible cycle operating a heat pump, then this becomes 1 over 1 minus TL over TH. And that sets the maximum possible performance for this heat pump. This is always true, whether it's a reversible heat pump or not. This first expression is always true. And because the first law is always true, this expression is also true. It doesn't matter whether it's reversible or just one you or I might buy. Or this is only true if it's reversible. So if they want to know what's the minimum work input or something like that for the heat pump or a refrigerator, or they somehow tell you it's Carnot or some other type of reversible cycle, then this one applies as well. Same thing with the other ones we just looked at. Those reversible ones only apply if you know we're dealing with the best possible version of that device. Okay. Questions about chapter 6? Chapter 7 now. Look at chapter 7. Chapter 7 looks at the second law in all its glory. Right? We start here. Start with this idea that a change in entropy is always being greater than or equal to the heat transfer that causes that, dQ, LQ, divided by the temperature at which that heat transfer occurs. And we know this because our good friend Clausius figured out that if he went around a cycle and integrated everywhere that heat transfer occurred divided by temperature, he came to the conclusion he's always getting this negative quantity. He's always getting this negative quantity. What does that mean? Well, that means, let's say, because Clausius is looking at heat engines. So we take this heat engine here, we've just seen a little bit ago. He's saying if I take this heat divided by this temperature, because this is coming in, this is positive, and subtract from it this heat divided by this temperature, and anywhere else heat transfer is occurring. So assuming there's not much, if any, heat transfer occurring here or here, then all that heat is here and here. So add this heat divided by temperature coming in, subtract this heat divided by temperature going out, add that up for the entire cycle, I'll get a negative one. Because this being the lower temperature down here, right, and this being the negative quantity, so this being the lower temperature, this ends up being the larger quantity. So I'm dividing by a smaller temperature. So he's saying no matter what we do, this always comes out negative. Ratio of the heat lost divided by temperature is greater than the ratio of the heat in the lower temperature. How does that work? Well, he did find as he could build something more and more efficient, he could get it to be less negative. He could get it to approach zero, but he could never actually reach it. What we found today is this means that something is being changed, something's changing. What we've figured out is that relates back to the entropy, the chaos, the unpredictability of the particles. That's always increasing. It's always increasing greater than the quantity that causes that change. So this is in all its glory, this is the second law right here. Second law in its raw form. Right? Now, I'm not expecting you to do anything with differential inequalities. I'm not really expecting you to do anything with differential equations, but that's where it comes from. All right, so what do we do with that? Well, what we normally do is we say, well, let's look at this for a process from state 1 to 2. So I look at a process from state 1 to 2. That means I'm going to integrate this raw differential inequality up here. So if I integrate ds from state 1 to 2, this just becomes delta S. So it's S2 minus S1. I'm using big S's there, total entropy. And that's going to be greater than or equal to the integral from state 1 to dq over t. We'll talk about what we do that with that guy in a second. Well, let's see if we can get rid of the inequality, which we can often do. And what we normally do is we say, well, let's change that to an equation, but let's do something where I save the rules. There's a rule here. Let's preserve the rule. So let's leave this integral from, I don't know why I keep drawing t there, from state 1 to 2 dq over t. Let's leave that one alone, but let's add something to it. So what we're saying here is there's always more entropy than what causes the entropy change, meaning there's entropy being generated. And that's what we add to it. So, well, that entropy generated, that preserves the rule. We just say, well, that entropy generated is always positive. If it's negative, that tells me I'm destroying entropy. And again, we don't think we can do that. Oh, yeah. We don't think we can do that. For certain, this is the law. So this becomes the most common form of the second law that we will use, because a lot of times we're working with a process from state 1 to 2. This is pretty easy to work with. We've talked about, well, how do I manage this? Well, we said you can find S values for water in R134 in the property tables. You can use this to figure out your change in entropy. If I know enough about this guy and I know enough about this guy, then I can use this to measure my change in entropy. Or I also have what we call Gibbs equation. Gibbs. Named after a special agent from TV, some scientist guy. Gibbs equation essentially tells us that a change in entropy is going to equal a change in internal energy divided by temperature plus pressure times the change in specific volume divided by temperature. Derive this guy. Or it's also equal to a change in enthalpy divided by temperature minus
specific volume times a change in pressure divided by temperature. This is a little s. These are all little variables, except for pressure and temperature. These are all, well, all these are what we call intensive properties per unit mass. Now, what we do is we say, well, again, differential equation, how much are we going to use it? We're not going to use it directly, but let's get it to something that we can use it for. So we think about what are some situations where I know how internal energy changes, temperature and pressure, volume and temperature relate to each other. An ideal gas. That's a common scenario where I know how these variables all interrelate. So for an ideal gas, we know the change in entropy. What we'll do is we'll say this is approximately equal to C sub V at the average temperature times the natural log of T2 over T1. This one's going to be plus R ln V2 over V1. This is an approximation because I'm assuming a constant C sub B at the average temperature. Assuming that C sub B is constant. Otherwise, I need to integrate C sub B as a function of temperature. But if I assume it's constant, which is a fair assumption in most cases, then this approximation works. We could also use it, and by the way, this form works pretty well if I've got a closed system where I'm probably going to know those volumes or the specific volumes easily. I can use it for control volume. If I've got mass flowing through it, if I can get to the specific volumes easily. Most of the time, if I'm dealing with a control volume, I'm probably going to use this other form that uses pressures. They're both true, they're both valid. The change in entropy can be approximated by C sub P at the average temperature times the natural log of T2 over T1. And this one's going to be minus R ln, and this one is P2 over P1. So again, that's an approximation assuming a constant C sub P average. I don't necessarily have to use that form. There is, we talked about this idea of you can use table properties in place of C sub P and delta T. I can use table properties and then it becomes an equal sign. There are these S circle, or I call them S degree values. I think the technical term is S circle in the tables. I can say this is delta S is equal to S circle 2 minus S circle 1 minus this R ln P2 over P1. Because again, what I have to do here is replacing this with C sub P dt. And I'm integrating C sub P dt over T, and I get this here. Right? So this represents the integral of C sub P dt over T. If I assume C sub P is constant, this becomes C sub P ln T2 over T1. But I don't have to do that integral. I can just simply say, well, I can use these table properties at the different temperatures. If I have rows in my tables for those temperatures that I've got, this works pretty well. If I don't, then it probably is a little bit easier to find a C sub P average. If I don't know both temperatures, it's probably a wash. I'm going to have to guess and check C sub P averaged back and forth between the unknown temperature to use this form, or I'm going to probably have to interpolate between rows to get one or both S degree values. So either method works just fine. We've seen that in class. You just have to be prepared for that. So if I don't know both temperatures, this gets a little trickier, but not impossible. We've got some ways around. What else then? So we did talk about, we did mention also, Gibbs equation can also be applied to solids and liquids. And that's where S2 minus S1 we can approximate as, in this case, C sub P at the average temperature times the natural log of T2 over T. Again, this is assuming constant phase.
liquid staying a liquid or solid staying a solid. If the base changes, it's not impossible, it's just the problem becomes a little more complicated. Questions so far? So, what are we talking about? This second law for a process from state 1 to 2. Gibbs equation allows us to quantify this left-hand side. If I've got an ideal gas, or if I've got solids and liquids, this works actually pretty well. It's one way I can quantify this left-hand side. I can also quantify the left-hand side if I know or understand what's going on with the right-hand side. I know what's going on with the right-hand side. So again, your text likes this nomenclature, this integral dq over t. What do we do with that guy? I'm not expecting you to do partial integrals. So what do we do with it? Well, common thing that might happen is it's adiabatic. What happens if we add up a whole bunch of zeros? We still get 0. So if I add up all the heat transfer and all the heat transfer is 0, then that sum becomes 0. The heat at a constant temperature, then this integral dq over t, the temperature comes out of the integral. This now becomes 1 over t integral of dq. And this just becomes essentially the sum of q net n divided by the temperature at which that heat transfer occurs. And we also said Sgen, what to do. There's 3 main things that we're going to do with Sgen. Right? If it's reversible, they somehow tell you this is the best possible version of the device. Maximum output, minimum input, nozzle, it's like maximum exit velocity. Something about it says, hey, this is, you have to think about what the device does, and they're telling me this is the best version of that device. Then they're telling you it's not generating entropy. It's the best case scenario. Now, a lot of times, you know, if they're asking, hey, is this a perpetual motion device? Well, they're either asking you to go back to those, if it's a chapter 6 type problem, they're asking you to evaluate the reversible performance and compare, or they're asking you, is it destroying entropy? Do you have a negative entropy generator? Or they may just simply ask, hey, tell me what's the entropy generator. It's possible that they could be given. It's kind of a strange scenario to me, but I've seen it before. The problem, the textbook problem, they've given you the Sgen. Most likely it's one of these 2 scenarios. It's either reversible, which you're looking for. Same thing with this guy, right? It's one of these first 2. It's one of these scenarios. Typically, it's either adiabatic or I've got some heat transfer granted at constant temperature. In the weirdest scenario, I think there was a problem in the homework where they gave you that quantity. You know what it was and how to deal with it. So those are kind of the common scenarios there. So where would we see something like this? Heat at a constant temperature. Well, if we look at for a reversible heat engine. All right, so if I look at a reversible heat engine, I'm not going to draw the whole diagram out. We've already drawn it once, but we'll draw this. We'll just say we've got a heat engine, HE. It's absorbing heat, QH, from a high temperature source. It's pulling work out. Right, we're pulling out QL to the low temperature source, and we're putting a little bit of work in to do it. So we look at this reversible heat engine and we say, well, we look at the change in entropy. Delta S is going to equal this integral dq over t plus S gen. We've already said it's reversible, so it's not generating entropy. And we're going to say that S2 equals S1 because it's a cycle. So for this thing to operate perpetually, we need it to return. We need the refrigerant as it goes around the cycle, or the working fluid in this case, the steam in this case, to return to its initial properties for it to operate in a cycle. So that means 0 is equal to this integral dq over t plus 0. We say, all right, well, if I go around this cycle and I add up all the heat and divide it by the temperature at which it's occurring, so this now becomes 0 is equal to, well, here I'm putting heat in. So that's positive, that's QH, and that's divided by that high temperature, TH. And down here, I'm removing heat at the low temperature. So it's QL divided by TL. So that's negative. And then again, it's not generating any new entropy. S gen 0. And notice what happens. QH over TH then is equal to QL over TL. And if we accept the second law as true, then that means that the ratio of QH over QL is equal to the ratio of TH over TL. Which is how we know, again, this is not the best way to prove something. I'm making this assumption based on the fact that that assumption is true. This is mechanically how it's going on. That's the reason we say this ratio is equal to this ratio early. Because if this is all true, and it's a reversible heat engine, this should equal this. That means this should equal this. Questions? My notes, I think those are big things. That should be chapter 6 and 7 in a nutshell. Short of isotropic efficiency, which we'll talk about just shortly here. I'm going to stop recording there.